Okay, I planned to cover this with a very broad view, so I apologize to those of you who have followed this area for the last several years. So I want to talk about start with talking about energy flow and how this is driving, at least overall, some ideas about the detector concept and calorimetry specifically. Then I'll talk a little bit about how well we can do with this, a few words about the physics, why do we need good jet resolution, and then a few words about current concepts and designs that people are thinking about. And then finally, the most important part, work to be done. I'd like to echo what Keith Riles just said about our goal here is to build a detector that's much better than the current generation of detectors that are on the market in E+, E-. So let's see if we can do that. Okay, energy flow. The basic idea is fairly simple. I've tried to illustrate it here with this sort of cartoon. And here's sort of a typical momentum distribution for particles in hadronic events. It doesn't change very much if you change the process. And you can compare that now to the resolution curves that you typically get for one of these excellent tracking devices that people are thinking about, as Keith just talked about, compared to the resolution in calorimeters for charged pions. Okay? And you can see the tracker wins. And if you couple that with the fact that in hadronic multi-jet events, about 2/3 of the visible energy is in charged particles typically, then this is obviously something you want to exploit. Okay? So the idea then is very simple, to use the tracker for the charged particles, because you can do better, do the photons in the calorimeter and the neutral hadrons, which are going to be always the hardest part. But at least it's a small fraction of the visible energy. This requires, however, to carry this out, dense calorimetry that's very granular. Okay? And so that's the direction that we're thinking about for these detectors at the moment. Okay? One figure of merit for, at least on the electromagnetic calorimeter, which I'll use later on, to describe how well you need to do is BR squared, the Sajida of charged particles, separation of charged and neutral particles in jets, okay, where R is the radius of the calorimeter, B is the V field, and divided by the molar radius, how well in the detector you can actually separate these guys out. Okay, so the emphasis here is on doing jet physics. Additional benefits are that you can do the things that you think you can do well. You can still do those. Excellent electron and photon position reconstruction. Non-pointing photons, I'll say something about that a little bit later. You have a muon tracker. And one question to keep in mind here, which is something that people often ask, is how good does it really need to be? And that, of course, relates to the cost of the device. Silicon tungsten has been used in luminometers at E+, E- colliders now for a while, but really only there primarily. It hasn't been implemented in a big calorimeter to date. But this was proposed as an energy flow electromagnetic calorimeter in '96 snowmass, and it's really been pushed very hard in Europe since then. By '99 or so, the standard Tesla configuration included silicon tungsten electromagnetic calorimetry. Okay? And what's even, I would say, newer is the idea of using a digital hadron calorimetry in concert with the silicon tungsten. Okay, I'll say a few more words about that in a moment. One way of looking at this energy flow business is from the point of view, as you just heard, and you've been hearing earlier today from Tom and from Keith, is that we're going to need a large B field in these detectors in order to get rid of the pairs, and so we can do excellent vertexing and flavor tagging, right? And when you have a large B field and you want to do good tracking, so you have a fairly large radius for your tracker. And once you do that, then that messes up traditional jet physics where you say use compensation for your calorimetry. Okay, and you'll see some illustrations of that. And so one point of view is that you're going to be doing energy flow anyway because of these other reasons for building the detector this way. Okay? And so the question comes down to how good does it have to be. Okay? Here's a couple of pictures. This one shows an event display from Tesla showing the electromagnetic calorimeter, part of an event, hadron calorimeter. And here's an example blowing up a tau decay. Tau goes to rho nu, where the rho decays to pi plus, pi naught, gamma gamma for the pi naught. And you can start to see with a sort of segmentation, the separation of the two photons and the charged pion. Okay, digital hadron calorimetry. It's clear that, it's generally true that if you have sufficiently small segmentation, you can go in and read out with just one bit. You can always do that if you push the limit. But of course, hadronic showers are sufficiently diffuse, so that makes it practical to think about doing that at the scale of, say, 1 centimeter of segmentation. Okay? And so that would allow you at that level to use cheap detectors to read out the hadron calorimeter. So that's part of this idea, but also it's quite interesting that people have started looking at this, led by the Europeans, that you actually can do perhaps better using this technique. Okay? Here's a simulation from Vido. This is just single charge pions. Here's adding up the analog sum of energies, and you get something like 44% over square root of E. And just counting the number of hits is this green curve. And then he makes a neural net and does a little better. Okay? So this is quite an interesting idea, and it's worth pursuing this for general interest as well as for linear collider. Okay, what determines the transverse segmentation that you need? And I'm going to concentrate here more on the eCal part of it, electromagnetic calorimeter. For a detector with a given magnetic field and radius, then you can ask the question, well, how well do I need to segment the electromagnetic calorimeter to achieve separation of charged and neutrals? Okay. And of course, this is also the physics comes into this, right? Because you need to know how close the particles are to each other. And so here's an example of that from Masako, showing that, okay, if you go out to your calorimeter, you have your cluster. This is with full simulation. Okay, now you ask the question, where is the nearest charged particle to that cluster? In the Monte Carlo, of course, when that charged particle is a pion, that's what really this is, then you're on top of that to within a few millimeters. But if it's a photon, then you're separated, right? And that separation, then, you can see here, you want to do, this is the scale down here, here's a centimeter, okay? So you want your segmentation to be on order centimeter or better. And you also want, therefore, your Moliere radius to be of that order, okay? Okay. What sort of jet resolution can be achieved? We've been using just the simple process, E plus E minus goes to QQ bar is sort of the standard candle to look for these studies. And here's an example from the Europeans showing the resolution they achieved with a fairly realistic simulation in the Tesla detector. And they're achieving about 30% over square root of E, okay, their device. I'll talk about what their detector looks like in a minute, okay. This can be compared to Aleph using basically similar people, similar techniques, I guess, about 80% over square root of E, okay. Now, one could ask the question now, how well can you do? Because this process, the idea is very simple, but actually carrying it out is fairly complicated, and it involves developing a lot of new tools that most of us don't have in terms of pattern recognition and so forth, okay? So clustering, tracking, and pattern recognition, merging tracks with clusters, and so forth. So you can ask the question then, how well could you do? Is this 30% limited by the device, by the physics, or by the algorithms? And so you can do a simple study just assuming, okay, what's the ideal? All right, if you take, in this case, I use the SD detector, okay, and just assume perfect charge-neutral separation, okay? So you have a perfect separation calorimeter, and then you have single particle resolutions and so forth. You use the tracker for the charged particles. And then you get something like, can you see this over there? Yeah, 15% over square root of E. Again, this is using no constraints, kinematic constraints or anything. So there's something like a factor of 2 just in developing tools. I don't know if we'll be able to exploit that. Some of that may never be able to be exploited, but that's sort of what you might be able to achieve. I think I'll skip this one, just multi-jet masses using the same idea. It's interesting then just to compare the same ideal energy flow to what you could achieve with an ideal compensating calorimeter, okay? So if you play the same game and say, I have a compensating calorimeter, it knows exactly what response and resolution to apply to every particle, and I reconstruct jets, okay? So this is now mass resolution, E plus E minus goes to QQ bar, and here's the energy flow. Here's the compensated calorimeter. There's a 5 Tesla field in this detector. Particles are going all over the place, and it's just hard to do this. So there's a big factor. So the skeptics now would say, in E plus E minus, there's beam constraints and so forth that you can. Do you really need this good resolution for jet reconstruction? Because you can play the card of the beam constraints and in a lot of processes do very well even without such a good device. Okay? And I think we need to work a lot on this question. I'll address that here in the next few slides. We really need to expand and provide a lot of detail in our list of physics benchmarks for looking at calorimetry. Here's some examples, and you've heard many of these earlier today. Michael emphasized the point of, in Higgs physics, looking at separating the Higgs final states in the case where Z goes to QQ bar in the ZH final state. I think you're always going to want to do that, all right? And do the best job you can. For a higher mass Higgs, separating out the decays to ZZ versus WW. There's sort of a class of processes here that have been discussed already today at some level. Multi-jet events, where you need to take a lot of care in reconstructing the events, number one, but also they have low cross-sections. So you're not going to be able to afford throwing away 60% of the events because they have hadronic final states or something like that. You want to try and get all of them, okay? Another class is in reconstructing things like top and TT bar WW for extracting anomalous couplings. Okay, you want to reconstruct these objects precisely, and you need to get angles precisely. Okay, if you want to get down to this sort of 1% that people have been talking about today. In SUSY, you want to be able to reconstruct these decay chains, and there's also, we've heard about single photon final states, and also in the case of SUSY, there's some cases where you have a single photon coming off from a detached vertex, right? And so the nice thing about one of these very granular devices is you can actually reconstruct that photon, get its position, and point it back, right? And you can do that quite well. This is a Tesla study, just as sort of a cute demonstration showing K naught to 4 gammas, reconstructing the decay vertex, and actually extracting the correct lifetime just using the calorimeter. Okay, here's a slide from, if you can see that, from the Europeans showing some of these same physics processes I talked about. And they've looked at a number of these that I mentioned already. One that Michael mentioned, this is a different study than the one he mentioned, was this case of the Higgs self-coupling. And going from 30% over Rudy to 60% over Rudy, you change your signal from 6 sigma to 3 sigma. Okay? A very interesting one, too, is in the case, obviously, if you don't have the beam constraints, like in T-channel processes, like these, then, obviously the jet resolution is going to buy you a lot. And there's a nice study done by Vidot showing this quite well. This is at 800 GeV center mass. Okay? And so this is separating out WWZZ final states. So you're making 2 jets going each way and forming their masses on the 2 axes. And this is for 30% over Rudy jet resolution. You can separate them out. At 60%, you cannot. Okay? Okay, so I would like to see these cases built more than they have been. But, we're exploring the unknown, so we should be ready for that, right? And, sort of a motherhood statement, at least from my point of view, is that a major advantage of E plus E minus is the access to all these states, all right? And so that's sort of what complementarity is all about. And so I think that we can take advantage of this environment. We should probably do that. So let me spend a few minutes going through the designs, what people were thinking about. The Tesla design looks something like this. The radius of the electromagnetic calorimeter is at about 1.7 meters, as shown there. They actually have 2 structures for their silicon tungsten calorimeter that they're looking at. This is an earlier version showing 40 layers in all, okay, longitudinally. And they have a more recent case trying to economize, going down to 20 layers, only 1,700 square meters of silicon. The segmentation is 15 millimeters on a side, about 0.5 millimeter thick silicon. Right now, for their prototype, they're thinking about 16 channels per readout chip. Okay, I'll try. And they'd like to increase that. For the hadron calorimeter, they've got 2 options that they're considering. This digital approach, possibly using RPCs, resistive plate chambers, as the detector. Another one involving scintillator tiles. Here's a few pictures. Here's the tiles that I just mentioned, scintillator tiles. Here's a part of a module detector slab for the silicon tungsten calorimeter, okay, as they're thinking about it. 2 layers of silicon for every layer of tungsten within this module. They bring the signals out on Kapton to electronics over here, so it's sort of invisible from the IP. One thing to keep in mind here is this is about a 7 millimeter or so gap here. That's important. There's these 2 simulation detectors that we've been talking about in North America, SD and LD, you've heard something about. SD, silicon tungsten, and probably digital hadron calorimetry. It's just on paper, right? And LD, same thing, except here it's scintillator and lead sandwich. Let me try and go through this rather quickly, SD and LD. The idea of SD is to do high-quality energy flow. Superficially, at least, it looks a lot like Tesla. The BR squared figure of merit in Tesla meter squared over centimeter, okay, is something like 5, that figure of merit in those units, similar to Tesla. Silicon tungsten electromagnetic calorimetry, we've been thinking a lot about this the gap size for the readout, because that affects the molar radius very directly, and about ½ centimeter segmentation, okay, and so forth. Another thing to think about, again, this is, on the order of 1,000 square meters of silicon. One of the things you want to avoid in these detector designs is to have everything scale as the number of channels, right? Like electronics. There'll be a talk tomorrow from Marty Breidenbach addressing this issue. And also, of course, a very important issue is the cost per square centimeter of silicon. For the hadron calorimeter, granular, possibly digital, and a number of people are starting to think about this quite seriously. What are the detectors here? There's a number of fundamental questions here. Does the idea even make sense? For LD, the philosophy of this detector is something written down on paper. I don't know if it makes sense as a real detector. It's a little unclear. It has, this figure of merit is high, but the segmentation is rather coarse. And on the other hand, it's got a 4-to-1 ratio of lead to scintillator, which makes you think of compensation. So anyway, I don't want to spend the time going through all the details here, but I think it's quite important to have a detector that we're simulating that's an alternative to, say, silicon, tungsten, and so forth, right? And but I'm not sure this is the right one at this point, so we might want to revisit this. So we have some tools that are working and ready for people to play with. Here's an event display in the Gizmo root framework, TT bar 500 GeV SD detector. This is TT bar goes to 4 jets with muon neutrino. Here's the muon. See that going through the hadron calorimeter. Okay, let me spend the last 3 minutes. Oh, okay. Well, last 1 minute. Talking about my take on what's the critical R&D. And, I think the main point I want to get across here, and we're not going to have time to go through this, is that we've just scratched the surface, okay? And there's just lots of good stuff to be done here. And I think a lot of it's quite interesting. I already mentioned physics simulations to some extent. We need to further build the case. General concepts. I already mentioned some of these, hadron calorimeter or not, so forth. If you're thinking about a calorimeter at a low energy IR, you can probably forget about this and just go back to the LEP SLD sort of standards. Software development. This is very important. We need this basic set of tools so we can evaluate energy flow performance. We're getting there. We're not quite there. And it's similar in Europe. I mean, they have some tools. It's not quite an integrated package yet. Okay? There's a lot of work to be done there. And then on the hardware, there'll be talks about this in the parallel session. Silicon, detectors and readout, there's a lot of important issues. And then this question of digital hadron calorimetry, I think, is very interesting. And, of course, we need to coordinate our efforts internationally. So let me just finish by advertising the parallel session. Most of these talks are addressing points that I raised here. I just wanted to point out there's one different talk. Ren Wan will be talking about possibility of crystal calorimeters at linear cloud. I didn't talk about that. Okay? And then we have a joint session later in the day tomorrow with simulations. I'll stop there.
Okay, just one question then, please.
I'd like to just make a comment. One of the topics that should be included is timing, especially for non-pointed photons. Repeat the comment.
Yeah, the question was Uriel was just emphasizing the need to study timing as an issue in calorimetry. In particular, he was mentioning the non-pointing photons, but I think in general it's something that needs more attention.
I have also a quick question, which is you talked about the best calorimeter, the best detector getting 15%. What goes into the 15%? What defines that?
Well, it comes down to just single particle resolutions then. And so it's dominated by the resolution of neutral hadron reconstruction.
It's still dominated by
Yeah. It's only 10% of the visible energy, but, it's hard.
Only if you're quick and short.
Very quick. The fact that gas detector have a good resolution on a digital basis was known since the SLB. The problem there is density within a jet, because you might lose hits and miscount because of that. Because of density. So that's something which has to be appropriately R&D'd.
Yeah, no, I wanted to emphasize that this whole idea of the digital hadron calorimeter is just getting started, really, and whatever good ideas you have are welcome.
Okay, we break then for 15 minutes and reconvene 20 after. Thanks.